Welcome back. Today we're going to look at our first assembly language programs. What is an assembly language? The CPU only understands machine code, ones and zeros. But ones and zeros are tedious for humans, so assembly languages were developed to make coding easier for us. Assembly languages are closer to the hardware. They allow programmers to have better control of the CPU than higher-level languages. Higher-level languages abstract away from the low level of assembly languages and allow programmers to solve problems in a shorter period of time. MIPS assembly language was developed in the mid-1980s as an example of a RISC architecture. MIPS is often taught in computer science department because it's a well-designed, clean language that will show you how instructions are executed by the CPU. This is a screenshot from the Mars IDE we'll look at in a minute. Notice the syntax has color highlighting, green for comments and strings, magenta for assembler directives, which are not assembly language instructions, but directions to the assembler on how to convert this program into machine code. The colors red, blue, and black appear in code. Constants are in black, instructions are in blue, while registers, which we'll discuss in a few minutes, are in red and start with a $sign. MIPS assembly language programs have two sections, one for data and one for code. .data defines a section of memory for static variables. In this case, there's only one item, an ASCII Z or null-terminated string that's associated with the label MSG. .text defines the code section of memory. The code section in this program just consists of two system calls, one to print hello world and one to end the program. A system call is necessary for a program to do something it doesn't have permission to do, such as write to the console, think printf in C, or return control to the operating system. Think of the last syscall as like return 0 in C. This is the Hello World program in the Mars IDE that we'll be using in this course. The Mars IDE is just a Java jar file that you should be able to run on any system with Java installed. If you Google Mars MIPS, you'll find a link to download it. The two basic screens are Edit and Execute. The buttons and menus at the top are fairly self-explanatory. You can resize the windows around the perimeter. And these up and down buttons can help you resize this bottom box here. Earlier we talked about a data section holding static variables, so let's see how it stored this string. I'm going to hit the assemble button here. And we see our string here. Notice I have the ASCII button checked. The string looks a little backwards because it stores the first character in the low order byte. Now let's run the program by hitting the green button. And we see we got our output here, hello world. On the right side of the screen, you'll see the registers. Registers have a name and a number, and here you can see their value. In Mars, we looked at the registers, but what is a register? A register is just a section of memory inside the CPU, very close to the ALU, the arithmetic logic unit. Because registers are inside the CPU, they can be accessed very quickly. Think of it this way. Is it faster to get your keys from your pocket, or digging around in your backpack, or searching your entire house? No, it's faster to grab them nearby from your pocket. Likewise, the ALU can grab information quickly from registers. In higher-level languages, we use variables to hold data and addresses. In assembly language, we use registers. Here's a block diagram of the inside of a Pentium CPU. Notice that the registers are very close to the ALU. This is common across different architectures. Here's another diagram showing the proximity of the register file to the ALU. The book sometimes uses generic register names like R1, R2, and so on. Here's an actual MIPS instruction using real registers T0, T1, and T2. The T is for temporary register, one that we just temporarily use to hold data. The $sign is used to indicate that this is a register. This is a MIPS integer add instruction. The comment tells what it does. It adds the contents of register T1 and T2 and stores the sum in register T0. All arithmetic and logic instructions have this format. First, the opcode tells the ALU what to do with these operands. There are 3 operands. The first one is the destination operand, and the second 2 are source operands. The destination operand is sometimes referred to as RD, and the 2 source operands are sometimes referred to as RS and RT. MIPS has 32 general-purpose registers. Each register is 32 bits, which is 1 word or 4 bytes. We most often use the T and S registers, T for temporary, S for saved. For now, we'll use these registers interchangeably. When we get to writing functions, we'll use them in slightly different ways. Another useful register is the 0 register, a read-only register that always contains 0. Here's another sample program. Within the data section, we see the .word assembler directive. Notice the 3 parts of this. We need a label so we can refer to it later. The label ends in a colon. And then we have the .word, which indicates to the assembler to reserve 1 word of memory. And then we have an initial value. An interesting thing about Mars is that sometimes if you don't give the word an initial value, Mars won't actually reserve a space for it. So always put something there, even if it's 0. So how are A, B, C, D like and not like variables? They're like variables in that they have a name and an initial value and a size, 32 bits in this case. They're not like variables because they don't have a type. The word could hold an integer or characters or other types of data. It's up to the programmer to keep track of what's in there. Notice we also have labels in the code. These aren't serving any purpose right now. They're just there for illustration purposes. Later, when we learn branches and loops, we'll need labels in the code. The Mars IDE doesn't require you to have a main label, but other IDEs do, and so it's customary to put it in there. Next, we look at MIPS load and store instructions. The store instruction copies the contents of a register into a memory location. The load instruction copies the contents of a memory location to a register. We'll use load and store instructions frequently. In fact, MIPS is often called a load-store architecture. The reason that MIPS is called a load-store architecture is that we can't do operations like add on memory locations directly. We have to first load memory locations into registers, then we can perform operations on them, and finally store the results back to memory. In this sample code, we see 2 new instructions, LW for load word and SW for store word. Load word copies the contents of a word from memory into a register, and store word copies the contents of a register into memory. So in this first line of code, we see that the contents of A, which will be 3, are copied into register T1, and the contents of B, which are 4, are copied into T2. Then we see that the contents of register T1, which is 3, are written out to C, and we see the contents of register T2, which is 4, written out to memory location D. All right, let's see how that looks in MIPS. In MIPS, I went to File, New, and then typed in the program. Notice that my Assemble button is grayed out. That's because I haven't saved the file yet. So let me save it. Whatever name you give it should end in .asm. And now I can assemble and run the program. First, let's look at the data section and see how these words are stored in memory. They're just stored as words one after the other, so we see 3, 4, 9, and 9. Now let's single step through the code and watch what happens to memory and watch what happens to the register file. So this first instruction copied the contents of A, which was 3, into register T1. The second instruction copied the contents of B, which is 4, into T2. The third instruction copied the contents of T1 out to memory location C, and notice that it overwrote the 9 that we had there. In fact, the only reason I put 9s there is so that we could watch these values being overwritten. The second store word copied the contents of register T2 out to memory location D. This is a different version of the program that we just looked at. Notice that I stored more than one item here after the dot word. This makes this function more or less like an array, where we have consecutive values in memory. We have a new instruction here, LA, for load address. So what these two instructions do is load the address of array 1 into T1 and the address of array 2 into T2. This will let T1 and T2 serve as pointers into array 1 and array 2. Notice the syntax for our load word is a little different. Formerly we had a label here. Whatever's the second argument needs to be an address. And when we have parentheses around a register, it means to treat the contents of that register as an address. So T1 is currently pointing to the 3. And so it will load the contents at that location into T0. And then we will go ahead and store that out to T2. And T2 will be pointing at this first 9 here. The second load word pair do exactly the same thing, except that now we're adding 4 to the contents of T1 and 4 to the contents of T2. Recall that MIPS words are 4 bytes, and that's why we add 4 to the address to access the second elements. This is the array version of the program, and keep in mind that there is no array, there is no such thing as a data structures. We're just treating these as if they're arrays. So let's first look at how these are stored in memory. We see it looks exactly like the first program. Array 1 has its 3 and 4, and array 2 has its 9 and 9. Now let's single step through the program. Load address loads the address of array 1 into T1, and we see that T1 contains 100, 10000. That is this address right here. Now we loaded the address of array 2 into T2, and that's 1001008. Which would be right here. Now let's load into T0 the first item from array 1, which is 3, and turn around and store that in the first location for array 2. Now we load into T0 the second item, which is 4, and store that out at the second location in array 2. Now I've got a practice for you. This is the first program we looked at in loadstore. I'd like you to modify this program to swap the contents of A and B. In other words, you won't need C and D at all. This is a little tricky because it's so much simpler than you're going to think of at first. So I'd like you to pause the video, code up a solution, and we'll talk about a solution in class. Next, we're going to talk about add and sub instructions. These are integer instructions. All MIPS arithmetic and logic instructions have the same format. We have the opcode, add, sub, and so forth, and we have our 3 operands, the destination register first and our source registers second. Notice the comments specify the operation. MIPS also allows for an immediate form of the arithmetic logic instructions that let you use a constant for the third operand. The reason for this is that small constants are often used in programs, and it would be inefficient to store and load these from memory. This simple program gives some examples of the addi instruction and also a new instruction, li, for load immediate. Load immediate lets us put a small constant into a register. So that is the first instruction in this program. We put 2 in register T1, then we add 3 to T1. Notice you can have the same register for both source and destination. And finally we add 4 to it. So now T1 equals 2 plus 3 plus 4 are 9, and this will be stored out at this location here, which initially had a 4 in it. Notice that Mars also implements a sub-I instruction. It's not actually necessary because your constant can be positive or negative. All right, I have another practice for you. I'd like you to write a program to load 3 integers from a data section similar to this, add them together, and store the result out here. You can initialize these locations to any value you wish. All right, again, I strongly encourage you to pause the video, code this up, and then we'll discuss it in class. Here's a little more challenging practice. I'd like you to convert this C expression into MIPS code. So give this one a try, and again, we'll discuss it in class. Next, we'll talk about MIPS syscalls. We've already looked at one of the syscalls. We've looked at the program termination call, and all of the syscalls follow this general format here. We load an integer into v0, and that integer represents the function that we want the system to do, and then we issue a syscall. Here's a demo of a few system calls. This is what it actually does. It prints out a message, please enter your age. Then it waits for the user to enter an integer. And then finally it echoes out the information to the user. Let's look at a demo of that. Notice in my data section, I have a place for age to be stored with an initial value. And then I have my ASCII Z strings for the prompts. I generally like to put the words first and then the ASCII strings later because words need to start on a word boundary. Here I have a series of system calls, one to prompt the user, one to get the integer, and then a couple to echo out the data. So how do you know how to do these system calls? Well, there is a help here. You can go to Help, and then you can go to System Calls, and you'll see the system calls down here. So let me move that to the side so we can see how these work. You always load the service number in V0. So the first one we see is service call number 4, which is print a string. This one expects a 0 to hold the address of the null terminated string. So that's why we used LA, load address, to load the address of our first message into A0, and then we say syscall. The second service call is 5, which is for reading an integer. Notice we don't have to send it anything, but after it runs, V0 will contain the integer. So before we run it, we put 5 into V0, and then we say syscall, and then after the syscall, V0 will contain the age, which we're storing out in memory. All right, we have another syscall 4, which will print out message 2, your age is. And then our last syscall is syscall number 1, which expects a 0 to hold the integer you want to print. And so that's why we use load word here to load the age into A0. Let's make sure that runs. So please enter your age. It just sits there and waits for the user to type in something and hit enter, and then it echoes it out. Let's see if we can break this. Let's run it again, and this time I'm going to enter my age as X. And I got a termination with errors because if we go all the way over here, we'll see that we had invalid integer input. So the only way we could get around that is to actually input a string instead of an integer, and then convert that string to an integer. We don't know enough to do that yet. We're going to make the very dangerous assumption that our user is actually going to follow directions. So we covered a lot of ground today: registers, opcodes and operands in MIPS, load and store instructions, add and sub instructions, as well as addi and subi. People who are successful in this course actually sit down and spend a lot of time coding, so I strongly encourage you to do that.